Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on linear algebra chapter Eigenvalues and Eigenvectors, lecture number 17, in which I will solve some more problems of this chapter. Now we solve a problem. Problem is, suppose S, capital S, is an n-row real skew symmetric matrix and I is the unit matrix of order n. Then we have to prove these four problems one by one. Now we solve the problems. Given that S is an n-row real skew symmetric matrix and I is the unit matrix of order n. Now we solve problem number 1. Since S is a real skew symmetric matrix, therefore transpose of S equal to minus S. This is number 1. Let lambda be the characteristic root of S. Therefore, the characteristic equation will be S minus lambda I determinant equal to 0. This is number 2. We know that the characteristic roots of a real skew symmetric matrix are either 0 or purely imaginary. Therefore, lambda equal to 0 or purely imaginary. Therefore, if we put lambda equal to 1, the equation two will not be satisfied. Therefore, determinant of S minus 1 into I not equal to 0 implies that determinant of S minus I not equal to 0. Therefore, S minus I is non-singular, implies that I minus S is non-singular. Proved. Given that A equal to I plus S I minus S whole inverse implies that transpose of A equal to I plus S multiply I minus S whole inverse transpose. This equal to, here we have the transpose of product of two matrices. So firstly we write the transpose of second matrix, then we write transpose of the first matrix. Second matrix is I minus S whole inverse transpose multiply I plus S transpose. This equal to, since transpose and inverse be commutative, so this will be equal to I minus S transpose whole inverse. Here I transpose plus S transpose. Since transpose and inverse commutative, this equal to transpose of I minus S is I transpose minus S transpose whole inverse. Here I transpose is I and S transpose is minus S. Since I transpose is I and S transpose is minus S is Q symmetric. This equal to I transpose is I minus S transpose is minus S whole inverse. Here I minus S, this equal to I plus S whole inverse I minus S. Let this is number 1. Now transpose of A multiply A equal to transpose of A is Y plus S whole inverse, and this is I minus S, and A is I plus S and multiply I minus S whole inverse. Let this is number 2. Now I plus S multiply I minus S equal to, since matrix multiplication is distributive, therefore we write I plus S multiply I minus I plus S multiply S. This is equal to I multiply I, S multiply I, S minus I multiply S minus S multiply S square. This is equal to I minus S square. This is number 3. Now I minus S multiply I plus S by distributive law. I minus S multiply I plus I minus S multiply S. This is equal to I multiply I minus S multiply I minus S plus I multiply S minus S multiply S. minus s square. Cancel s and s. So this will be equal to I minus s square. This is number 4. Therefore, from 3 and 4, we get that product of I plus s and I minus s is commutative. Therefore, from 2 we get here I minus s multiply I plus s is commutative. So transpose of A multiply A equal to I plus s whole inverse. Here we write I plus s. Here I minus s and then I minus s whole inverse. This equal to I plus s inverse multiply I plus s is unit matrix. Here I minus s multiply I minus s whole inverse is unit matrix. So I multiply I is I. Therefore A is orthogonal. Since for orthogonal matrix A, transpose of A multiply A equal to unit matrix. Proved. Number 3. Since in previous problem we have seen that I plus s and I minus s be commutative, implies that I plus s multiply I minus s equal to I minus s multiply I plus s. This is number 1. Pre-multiplying and post-multiplying. Both sides of 1 by I minus s whole inverse, we get I minus s whole inverse. Then we write this I plus s I minus s and post multiplying I minus s whole inverse equal to pre multiplying I minus s whole inverse. Then we write this I minus s I plus s multiply I minus s whole inverse, implies that here I minus s multiply I minus s inverse is unit matrix. So we write this to I minus s whole inverse I plus s multiply unit matrix. Here we get I minus s whole inverse multiply I minus s unit matrix. Then we write I plus s I minus s whole inverse, implies that this is I minus s whole inverse I plus s multiply unit matrix is this. Similarly, unit matrix multiply this is this. I plus S, I minus S whole inverse. Since A is I plus S multiply I minus S whole inverse. This is A. Implies that A equal to I minus S whole inverse multiply I plus S. Proved. Now we solve number 4. Given that x is a characteristic vector of S corresponding to the characteristic root lambda. Therefore, Sx equal to lambda x. This is number 1. Adding both sides with x, capital X, implies that capital X plus Sx equal to capital X plus lambda x, implies that I multiply x plus Sx, this is x, here we write 1 multiply x plus lambda x, implies that I plus S, here x common, x, here 1 plus lambda x. This is number 2 from 1. We get minus Sx equal to minus lambda x, implies that we add with x minus Sx equal to x minus lambda x, implies that I multiply x minus Sx equal to 1 multiply x minus lambda x, implies that I minus S x equal to 1 minus lambda x. This is number 3. Pre-multiplying both sides of 3 by I minus S whole inverse, we get I minus S whole inverse multiply I minus S x equal to 1 minus lambda I minus S whole inverse x, implies that this is unit matrix Ix equal to 1 minus lambda I minus S whole inverse x, implies that here we have 1 minus lambda, we take this left side 1 by 1 minus lambda x equal to I minus S whole inverse x, implies that y minus S whole inverse x equal to 1 by 1 minus lambda x. This is number 4. Now pre-multiplying both sides of 2. This is 2 by I minus s whole inverse. We get I minus s whole inverse, then I plus x capital X equal to 1 plus lambda I minus s whole inverse capital X. This is number 5. Using 4 in the right side of 5, we get I minus s whole inverse multiply I plus s x equal to 1 plus lambda I minus s whole inverse multiply x equal to 1 by 1 minus lambda x. 1 by 1 minus lambda x implies that I minus s whole inverse multiply I plus s x equal to 1 plus lambda by 1 minus lambda x. This is number 6. Since A is I minus s whole inverse multiply I plus s, we may write this as A x equal to 1 plus lambda by 1 minus lambda x implies that x is a characteristic vector of matrix A corresponding to the characteristic root 1 plus lambda by 1 minus lambda. Here this is the characteristic root and x be the characteristic vector. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button, and if you have not yet subscribed my YouTube channel, then please subscribe my YouTube channel. Thank you.